All right, let's take a look at what we got. He's got this thing where he takes like, what are they called whenever like every letter means something? It's not an anagram. Anagrams where you shuffle up the letters, right? Acronym. So he'll be like, team, together each achieves more. And he has one for failing. And basically it's like to enrich your learning process. But yeah, definitely I could probably hang with him. He seems cool enough. But it was between that and Steven Seagal Lawman. What are you gonna do? They were both in Under Siege together. I mean, have you guys ever even seen Under Siege? That's amazing. All right. Under Siege is where they try to take over a Nimitz class aircraft carrier with its Tomahawk nuclear powered missiles. Steven Seagal, you guys don't know who Steven Seagal is, do you? He's like a master of Aikido. He goes in and whoops their butt, but he's a cook on the Nimitz class. Yeah, right? He does some kitchen knife stuff. It's amazing. I don't know, maybe mid-90s, maybe early 90s. All right. Let's take a look here. So the last time that we met, this is continued from previous page. We worked through this equation right here. We had a zinc and copper. Of course you can't. I haven't hit the share button. Thank you. We worked through the zinc and copper voltaic cell. We found the delta G using this equation. Remember, N is the number of moles, F is Faraday's constant, and E is the standard potential of the cell. We found it was 1.10 volts. Remember, 1 volt is 1 joule per coulomb. And basically that's energy per charge. And this delta G is in joules per mole. We then, over here, we solved for K using the formula delta G equals negative RT, the natural log of K. So I think what we want to do now is we want to take a look at what if we change this? And that's right here. So this is standard energy potential. We know as a battery goes through its life, things change. If it's a rechargeable battery, they don't charge as well. If it's a battery that's been in your headlamp or something like that for a long time, then there are some, it's weaker in our mind, right? It's weaker. It may have died. Well, K from right here, K is at equilibrium. Q is at a point that's not at equilibrium, right? That's that quotient that we've talked about in the past. So K is at equilibrium, Q not necessarily at equilibrium. So let's imagine then we have in our equation up here, this is K, this is at equilibrium. Let's imagine that we have 10 molar copper solution, copper, copper 2 sulfate solution. And 1 mole, let's not do 1, let's do 0.01 molar zinc solution. In our minds here, which reaction would be favored? Forward reaction. Why? Yeah, unless the K for this is very, 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 very small, we've got a huge amount of reactants and a very small amount of product. So what would we assume the output of this battery would be? Would it be standard, less than standard, or more than standard? More, right? Because we're going toward the forward reaction. And we've already worked with this relationship before. We've already worked with this battery. We know that it is voltaic, meaning that it is spontaneous, right? If we got a huge amount of reactant and a small amount of product, we're going to get a higher voltage than normal for this. So let's go ahead. Not liking the amount of space I have here. Let's see if we can make it work. So the formula for this is E cell equals the standard minus. Now what they've done here is they've taken and made this at I believe the temperature. This is the 8.31 for the R, and this is 298, and we've got this 0.0592, which is the R times standard temperature divided by Faraday's constant already for us. We could put all that in, and we're going to multiply that times the log of Q. Minus 0.05. And what is in here? Number of moles of electrons, and how many moles of electrons are being transferred here? Is it 10? Good. Zinc is going to zinc what? And copper 2 plus is going to copper, so how many electrons are being moved? 2, right? And can I get this in here? I'm gonna have to make a little extension there. Log of Q. I wonder if there's any representation of the question mark. What's that? So if we take a look, you would actually have to create this if you don't memorize this, because it is not on here, but they do give you delta G, RT, natural log of K, which you could then sit here and rearrange delta G using the negative NFE and delta G equaling negative RT natural log of K. Basically set those equal to each other and then come up with this actually. I don't think this is something that changes very much. It hasn't? Let's see. So you will have that on there, and it is in it's on the 0.0591. It's in this format right here, right? Yeah. So then you would have to use the R constant, the one that deals with joules, the 8.31, and temperature, and then they give you also Faraday's constant. Should be good from there. All right. So the log of Q. If we take a look, the E naught standard potential, if we recall, was 110. So here's the major thing with this. We're going to have 110 minus this whole thing, right? If we take a look here, 110 minus this whole thing, how much do you guys know about natural logs. If Q is greater than 1, the natural log will be what? Right. So that means that we will be subtracting a number. And if Q is less than 1, right. So whenever we look at Q, remember it's products over reactants. So if we take a look here, 0.01 divided by 10 is a big number or a small number? Small number. That means it's going to be less than 1 or greater than 1. Less than 1. That means that the natural log of that is going to be negative. When we subtract a negative, we are actually doing what? Adding. So if we're favoring the products for this, then the cell potential is going to be greater than it normally would. This makes sense? If we're favoring the reverse reaction, the cell potential is going to be subtracting a positive, which means it will be smaller than it normally would. Just roll your eyes at me. So let's keep that in mind. In reality, that's going to probably be, I think everything I've read at this point, I think it's actually funny that they put that equation on there. That's awesome. But I don't think that they're going to have you necessarily work this equation as much as we'll probably do 2 or 3 problems and then you can practice it on your own. But it's going to be more conceptual than that. It's probably going to be answered in a multiple choice fashion versus the mathematics behind it. But that's the idea. Those are the concepts. So we have got minus 0.0592 divided by, what's our n here? 2 times the log of 0.01 divided by 10. Let's point 0.01 divided by 10. Log answer times, and let me do that again. Log answer. What do we see there? The number is what? Negative, right? So then we're going to take and multiply that by 0.0592. Divide that by 2. And then we're going to take 1.10 minus the answer. And we will get 1.19 volts. 1.19 volts. Does that make sense? Is the battery more energy projecting? Yes. Why? Again, we have more reactant than product. It's going to force it forward. Question? You all right? Did you roll his eyes at you too? I saw it too, right?
I am back.
I made them up. Basically, I said that this is 10 molar copper 2 sulfate solution, and this is a 0.01 molar.
Oh.
Yep. So I came up with these 2 numbers just to talk about the concentration of the solution in each of the half cells, right? Yeah. So if we take a look here, as I put here, you should not really have to put that formula in there, but as it says 2019, they put that formula in there for a reason. Again, the beauty about that is that that reason could just be so you could see the formula, right? And then mentally do it. But the reasoning of this is basically the value of Q. As we said, more reactants, so products are favored, will favor a forward reaction. More products, reactants are favored, will favor a reverse reaction. If we're favoring the forward reaction, that means that products over reactants, it says more reactants, so we'll have a bigger number on bottom, right? To favor the forward reaction. That means Q will be less than 1. That means you're subtracting and something that is a negative. When you subtract a negative, it actually is bigger. If the reactants are favored, that means you have more products. So products on top would be a bigger number divided by a smaller number. That means your Q would be greater than 1. So you would be subtracting a positive number, which would result in less voltage. And we know this as the life of the battery goes on and on and on, we end up with more products, and what happens to the voltage of the battery? It goes down, right? This is whenever we say the battery is on its last cycle. Conceptually, that hopefully makes sense with equilibrium. Give me your best eye roll. I love how everybody looked to see what your best was. You were going to be judged so harshly. Don't do it anymore. I don't want to put you under that pressure. It's not fair to anyone. But I bet you could do a good one. Yes, yes, yes. Home players. Am I been muted this whole time? That would be embarrassing. Dylan, you did?
I used to have a I will laugh.
Yeah. I did it so much as a child that it's now painful for me. What is that? Like when you have a pre-existing injury from your eye rolling. That's kind of amazing. All right. You guys know the old formula. What's the symbol for current? Is that on there? Huh? Yeah, not the unit symbol. Who said that? Brilliant. It is on here. I equals Q over T. What's Q? Yep, charge. What's T? Time. Yeah, right. Yeah, T is time. So we know Faraday's constant. So this is kind of where, I mean, in reality, like there's a bunch of schools of thought or whatnot, but everybody says that physics is math and chemistry is physics and biology is chemistry. I don't know if you ever heard that, but basically that's the way it goes. So this is one of those things of where you can see direct ties into your physics education versus your chemistry education, I'm assuming. And there's probably been many, many more. I mean, I wasn't a physics major, so I don't know all the ties. I think I took 4 physics classes or whatnot in college. I had like 8 o'clock labs at night. They would last until 10, worst class ever. Whew. Current equals charge divided by time. So we know that current is charge divided by time. Charge is measured in coulombs. Time is measured in seconds. This is all equal to the unit for current, which is amps, right? Faraday's constant is a charge carried by 1 mole of electrons. That's important because if 2 moles of electrons are required, that means you would need to double this, right? Or if you have 2 moles of electrons, you would need to double this. So basically what we're going to do is some amazing dimensional analysis here using this idea. So a car battery is listed. I like the fact that it says listed because that's actually still kind of going on today. When I was a kid, you had this magazine called the Wheeler Dealer. And when you were like 14 or 15, you looked in the Wheeler Dealer for the cheapest car possible so that when you turned 16, you could find a crappy job that you could get to and go and like how much you would make and which car you could buy. The Wheeler Dealer listed these cars. And as it says, the car battery here is listed as having 475 cold cranking amps, which means that it can produce 475 amps for 30 seconds. If the reaction is this for the lead battery, how much lead is consumed in 30 seconds? So what do I want for my final answer? Oh, wow, you guys are like, yeah. Come on, we can do better than moles. Grams, right? Can we get grams? Let's find the actual amount in grams of lead. Moles isn't going to mean much to anybody. Grams of lead. How many units does it have? Well, this is coulombs per second. This is charge per time. How many units is this? 1. So we want to start here with 1 unit. In reality, we know that 475 amps is actually 475 what? Coulombs per second. How many units is that? 2. So we don't want to start with that, do we? Bam. Good. Let's start with the 30 seconds. Well, we just found out that every 1 second is what? 475 coulombs. I have so much trouble spelling that word. Somebody's name, those of you in physics, is it like a Johnny Coulomb or something like that? Yeah, or did it just come up like, let's call it something ridiculous? So we have coulombs. We know that Faraday's constant can get us to moles of electrons. How many electrons for every mole of lead? 2. So every 9,648, 485.3 coulombs. I'm going to start abbreviating it like that. I can't spell it because I spell it differently every time. Coulombs, not coulombs, right? Is 1 mole of electrons. So that means it takes this many charges, this much charge, to get rid of 6.02 times 10 to the 23rd electrons. And every 2 moles of electrons is how many moles of lead? It's funny, we abbreviate moles with MOL, and then we abbreviate electrons with E negative. So it looks weird to me at least. And that's 1 mole of lead. And every 1 mole of lead is how many grams? 207.19. 30 times 475 divided by 96,485.3 divided by 2 times 207.19.
The answer is about 15.3.
15.3 grams of lead. How amazing is that? If you sit there and you, right? You try to turn that battery for 30 seconds. That consumes 15.3 grams of lead off the anode. What happens immediately thereafter? The engine starts, and what takes over the electrical abilities? The engine connected to the what? You guys know that thing that converts mechanical energy into electrical energy? The alternator. And then what happens back to that anode? The reverse reaction, as they pump electricity into it, it becomes an electrolytic cell, which then does what to that 15.3 grams? Deposits it back on the anode, right? So that this whole thing can come over and over and over again. Before the battery was invented, what was the method of getting that that amount of energy to the engine? Crank, right? The crank. So without that lead battery, you would have to sit there and crank that engine. If you're a model airplane, pilot or whatnot, you may have seen one of these where you actually have to take a stick and basically move the propeller or your finger, but like these type of things still exist. Questions there? So that electrolytic cell is basically the opposite of the galvanic cell. The galvanic cell produces current because it's spontaneous. The electrolytic cell requires energy because it's non-spontaneous. So the cell potential in an electrolytic cell, it's negative. So if you have a reaction like our zinc copper battery that produces 1.10 volts, if we wanted the reverse of that to happen, we did this with Olivia's quarter, right? We had the reverse of this happen. We deposited copper onto that quarter, right? If you wanted that to happen, you would have to you get the reverse reaction to occur. You'd have to have greater than 1.10 volts going into the system. What did I use? I used like a 9-volt battery, right? Yeah, we used a 9-volt battery in class to do just that. So, I mean, obviously we had that much. Using exactly what we did there. This is a similar problem from 1974. Basically, they want you to figure out, they give you grams. So you've actually got to go the opposite direction we did and go from grams to seconds because they want how long. You have to do exactly what we did, but go from grams to seconds. And then they're like, okay, we've also got this chromium thing. Well, that would be how much electrons how many moles of electrons for each mole of silver? What's the charge of silver? +1. So every 1 mole of silver requires 1 mole of electrons, right? How about chromium 3? 3 moles of electrons for that one. So for B, you're basically looking at the electron difference, 3 moles of electrons going in. And then for the last one here, they are having you do O2 gas at the platinum electrode. Basically, O2 gas is getting it. So every 1 mole of O2, actually, how many moles of electrons for O2 gas? Can you see that? No. O2 gas requires how many moles of electrons? 4. How many? 1 mole of O2 gas takes up what volume at STP? 22.4. Right? So this problem here, problem 3, is asking you to figure out what volume would be measured. Basically, you're going through several different processes for different numbers of electrons there. And then you're applying the gas law constant every, at SPT, every 1 mole of gas takes up 22.4 liters of space. A lot on this topic here. They're bringing back a lot of things. Questions? All right, let's have one last thing of fun. What? Roll your eyes at me. I dare you. What was that? That was a weird choice to make.
I did it.
Are you going to be doing things like that all day?
I didn't need to do that.
Right? All right. Take a look here. I got a huge mess. It's funny though. A little bit. All right. You guys see this? They have a piece of aluminum here, and it's got a zinc washer on it. Remember, I'm from the South. They call these washers. Have you ever heard that before? Isn't that crazy? Here I have a paper plate I cut up, and basically I'm soaking this in salt water. Yeah, remember we talked about Volta? This is the thing he made. I've got a piece of aluminum here because aluminum conducts electricity. I've got a washer, and I'm going to put a piece of this paper plate on top of that, and then I'm going to take and put a copper penny on top of that. Here I have a voltmeter, and I'm going to connect this. What's that? Oh, do you need to go somewhere? You sure? Your beautiful shirt. So take a look here. This is one piece of copper. Ah, dang it, it looks like garbage. This is one piece of copper. I don't even know how to focus this one. One piece of copper, one piece of zinc. Look at that. We getting anything? .5 volts. All I've done is lay a zinc washer with a paper plate that's been soaked in sodium chloride and then laid a piece of copper on top of it. We can sit there and stack more and more of this. Here's another piece of the paper plate, a piece of zinc, another piece of the paper plate. Yeah, right? It won't change the voltage, remember, because it doesn't matter how many moles we use. It's not going to change the voltage, but this one would last longer. We got maybe a little bit higher. I'm getting some interference. Come on now. But yeah, this is the first. There we go. This is the first time that somebody was able to make something that gives off electricity. I mean, what's the year of Ben? What's the dude's name? Benjamin Franklin. Like, I'm gonna take a key and put it on a kite and electric. Right? Volta made the first what we call voltaic pile, and then we had a way to have electricity that was stored. Now this allowed Joseph Priestley, allowed Joseph Priestley, but more What's the cooler guy than Joseph Priestley? It's on the tip of my tongue. Huh?
Edison?
No. It's the guy that like basically had to create the one-way street because of him. Because he basically attracted such a large crowd that in London they had to say, you know, we can't have this street going both ways. We need this to be a one-way street. He is the guy that found sodium, potassium, and all of this, and he used the voltaic pile. Who? Nope. What is it?
Henry Ford?
No. I don't think it's Henry. It's more exotic than that.
Humphrey Davy.
Humphrey Davies. There we go. Humphrey. So Humphrey Davies basically used the voltaic pile to find new elements, which was amazing. Joseph Priestley also found, like, I think he found more elements than anybody, but he basically found gases. Davies finding these alkaline metals using the voltaic cell from, again, potash, which became potassium, and soda ash, which he found sodium in. They were originally called potash and soda ash, and that's where the names potassium and sodium came from, strangely enough. I think that's enough for today, guys. For tomorrow, all I want you to do is that 1974 problem. Have a great day.